Hi there. This is second lecture in the series that we're doing talking about regularized estimation. Um, in the first discussion we had together, we spent time really thinking about what regularization is, what it's useful for, when we might use it, how it works, that kind of stuff. And if you remember, what we were really interested in when we're talking about regularization is this idea that we've got a lot of variables, a lot of independent variables in a regression model, an example we're looking at. And we need to try to deal with the large number of independent variables in a hopefully statistical way. And what I mean by that is we're trying to pick out the independent variables that we think might be the most important or most salient when it comes to our dependent variable, right? So that was our goal. And we went through the lasso and the ridge regression and the elastic net. And if you remember, in all those cases, we're basically applying a penalty. We're saying, all right, here is this penalty, this sort of tax that we have to pay for having a lot of independent variables. So the more independent variables we have, the bigger that tax is going to be. And so the flip side of that is those independent variables really better be contributing something useful to explaining the dependent variable. And that was kind of the crux of our discussion. And went through some examples and that sort of thing. So what I want to do, this is going to be a little shorter discussion, but what I want to do here is talk about inference. And when we talk about inference in stat world, we're really just saying p-values. So the idea is, how do we get p-values for regularized estimators like the lasso and the net and the ridge regression and so on, right? And so the p-value issue is not as simple as you might think it is. It's not quite as simple as just, well, we run lasso, we get our independent variables that are important, that have non-zero coefficients, and then we run regression and get p-values for those. That doesn't quite work, and we'll talk about why. So where are we headed in our little discussion here about inference? We're going to talk first about why hypothesis testing is a little different when it comes to these penalized estimators. Then we're going to talk about solutions for dealing with that. And in particular, we're going to focus on something called the covariance test. And then we'll look at what the covariance test tells us for the problem that we've been playing with. So when we think about inference, and again, just think, hypothesis testing, in regression, what we're typically interested in is whether a regression slope or a coefficient is statistically significant. And in regression, when we say the slope is significant, what we're really doing, as you can see in that subpoint of bullet point 1, is that we're really saying that the slope relating the independent variable j, whatever that happens to be, and our dependent variable is different from 0 in the population. That's really the crux of what we're doing. We're saying, well, in the population, if I could look at all the possible individuals who could be measured by my, in this case, the cognitive ability scale, and then look at the relationship between one of the K-bit scores and the waist verbal reasoning score that we talked about in the previous discussion. If I could look at all those people, would I find that the relationship between the K-bit and the verbal score is 0 or not? And that's this null hypothesis here, right? This is saying, well, that slope in the population, the Greek letter with no adornment, with no hat on, is equal to 0. That is the same thing as saying the two variables are not related. And that's really what we're after when we talk about inference, if you will. So in regression, what we do is we say, well, we're going to get an estimate of the slope for variable j. We're going to get an estimate of the standard error or the variability in that slope from one sample to the next. And that ratio becomes the t-statistic. And if this t-value here is big enough, then what we say is, oh, there is a relationship because the slope is really large, even when we consider the variability within the possible slopes we could get. And if the beta is near zero, and this t-value is very small, then we say, no, when we consider the variability in our sample betas, there's really not much going on, right? That the relationship is between the k-bit score and the verbal score is very close to zero, close enough that we say they're not related. So that's how it works in regression. Now, the problem is when we talk about regularized regression or these penalized models, we've got a little twist that we don't have with regular regression. And that twist is we have the extra step of variable selection. So if you think about how the lasso works, for example, the lasso basically, heuristically, we could say, is looking at the data and saying, well, the first thing I've got to do as the lasso estimator is I've got to pick out the variables that are important. So I've got to pick out the ones that don't have a zero slope, period. And then once I pick those out, the ones that are remaining, where the slope is something other than zero in my sample, those are the ones that I care about. And in regression, we don't have that step. Straight up standard old regression, we don't have that extra step. And so that's really what is going on, or what makes this regularized estimation a little bit funky. So we've got to figure that out. How do we calculate the standard error? How do we calculate a test statistic, really, that accounts for variable selection? That's the major problem. Now, if your primary interest is, I want to run lasso and I want to get some p-values, the next few minutes of discussion, you can be like, well, okay, that sounds cool, Holmes, whatever. And then, we'll look at some examples and stuff. But if you're interested in kind of what's going on under the hood, that's the purpose of this little digression, if you will. So over the years, folks who deal with regularized estimators have played around with a variety of possible approaches for inference, right? So there's Bayesian estimation, which works well. There's the bootstrap, which can work well in some cases. But recently, the most promising approach, particularly if you don't want to go the Bayesian route, if you want to go with Bayesian statistics, that's a whole other kettle of fish, and that we're not going to talk about that here. Not that it's not worthwhile; it is actually, I think, can be very worthwhile and powerful. But for the kinds of estimators we're talking about, we're not going to discuss the Bayesian approach. But a really promising approach is something called the covariance test, and it involves accounting for the lambda and or the alpha, those penalty coefficients, that the tuning parameters that we talked about in the previous discussion. So if you haven't watched the previous discussion, you probably want to watch that first before you get into this. And so inference, or getting p-values, is only going to pop up after we've gotten our final set of variables. So that's kind of the trick here, as you'll see. So when we talk about the covariance test and inference using it, we're going to get a test statistic called T sub j, so capital T sub j, for each variable j. So each of our independent variables, we're going to get one of these big T statistics. It's distributed as an F with 2 degrees of freedom, or two numerator degrees of freedom, and n minus p denominator degrees of freedom. So the n is our sample size and the p is the number of predictors. And basically, here's how it works. The covariance test says, well, how much additional variance does the independent variable I'm interested in, so one of the k-bit scores, variable j, how much additional variance in the dependent variable does it account for when it's added to the model? So basically it's saying, let's run a penalized regression with our target independent variable, and let's run it without the target independent variable, and let's see how much additional variance it accounts for. And if it accounts for a lot of additional variance, then we say, yeah, it's important. It's statistically significant. If it doesn't account for much variance, then it's not important. And there's going to be a trick, as you'll see in a second, for how we account for the the variable selection process. So we're going to be testing the null hypothesis, essentially that the slope is 0 in the population. More accurately, we're going to be testing the null hypothesis that x sub j does not contribute to explaining the DV. So you can have a case, as we'll see in our example, you can have a case where the lasso says, you know what, this slope is not strictly speaking 0 based on the sample data. But when we do the hypothesis test, it is essentially 0, from a hypothesis testing standpoint. In other words, we would say, well, maybe it's not estimated to be 0, but it's not important. Statistically speaking, it's not significant. So how does this work? This is the part, like I said, this is the under the hood part. It's kind of cool. So I hope you will, give it a listen. But as I said, you can successfully use this approach without necessarily fully, buying into or wanting to learn how the method works. But here's how it works. So let's just take one target variable, one of the k-bits. It's going to do this for every target variable, but let's just take one of them, right? So what this approach does is it says, let's find the optimal lambda for each independent variable. So let's say independent variable 1 in our sample. We're going to find the optimal lambda for that k-bit score. And for when that enters the model. So what value of lambda is associated with k-bit number 1 jumping into the model, right? And we'll call that lambda j. So we're going to estimate the slopes and the intercept for that lambda. So all the variables that would be included in the model at a given lambda for lambda j, we're going to estimate the slopes. The variables that would have been regulated out, that would have been zeroed out basically by the lasso, those don't get estimated. So that's step 1. We're going to call the independent variables that were in the model right before that. So the set of independent variables that were not zeroed out right before we entered the k-bit score we're talking about, x sub j, in the model, we're going to call those a sub j minus 1. That's a little subset. So that a sub j minus 1 includes all the independent variables that were in the model right before we included x sub j. Okay, and they would be associated with this lambda j minus 1. All right, so we've got the optimal lambda that brings in x sub j. We estimate the parameters for that, slopes and the intercept in step 1. In step 2, we say, let's take one step back. Which variables were in the model before we entered x sub j? And we'll call that set of variables, however many it is, a sub j minus 1. Then what happens is the lasso algorithm says, okay, now let's fit the lasso model only on a sub j minus 1, but using the lambda for x sub j. So let's think about what that's actually doing. It's saying, I've got the optimal lambda that brings x sub j in the model. That's lambda j. I've got this set of independent variables that were in that model before x sub j entered in. What I'm going to do is I'm going to estimate the slopes and the intercept for the a sub j minus 1 variables. So all the variables that were in there before x sub j jumped in. But I'm going to use the lambda that let me bring x sub j in. Okay? That's step 3. So now I've got essentially 2 sets of coefficients, right? I've got the coefficients that we had for when x sub j was in the model in step 1. And in step 3, I've got the coefficients that were in the model for the variables that were in the model right before x sub j jumped in, but using x sub j's lambda. Why would I use x sub j's lambda? Well, that's that variable selection piece. Remember, I mentioned that one of the problems with or issues to get around with the lasso is you have to, when you do inference with the lasso, is you have to account for variable selection. How do we do that? Well, we do that through this business of using the lambda associated with the x sub j, but on the variables a sub j minus 1, all the variables that were in there before x jumped in. All right. So now we've got two sets of slopes. What do we do with those? Well, that's what pops up here in this in this T sub j line. So notice this little bit of business here where I've got y, x, beta, lambda, j. That's the covariance, thus the name covariance test. This is the covariance, or the numerator of the correlation. This is the relationship between the dependent variable and the predicted dependent variable based on the variables in step one. And then we subtract from that the covariance, or the relationship between the dependent variable and the predicted dependent variable using the a sub j minus 1 variables, right? So what we're doing is we're saying, what's the correlation, or what's the relationship between the predicted y and the actual y when we include x? And what's the difference between the actual y and the predicted y when x is excluded? And that difference in the covariances, that's a measure of how important x is. So if the x sub j variable is super important, like it's really, really important in explaining why, then the covariance, the first covariance here, this first relationship is going to be a lot bigger than the second one, right? Because the first one says, well, I'm including information not just about the variables that were in the model before x, but x itself. And if that covariance is a lot bigger than the one when x is not in the model, that means, boy, x really contributes a lot. It helps us understand why. It makes that relationship between the prediction and the actual value for y big. Okay. And so then we divide that by essentially a measure of variance. But all the magic is happening in this difference right here. And so that's the covariance test. And what's cool about that is it reflects not only the coefficients, right? Not only the relationships between each independent variable and y, which is in these betas, but it also reflects the variable selection process because of these, the coefficients for the aj minus ones when we use lambda j, or x of j's lambda value, the lambda j. And so, like I said, this T sub j, we're going to get one for every independent variable, and it's distributed as an F statistic, and then we can get p-values for it just like you would for an F from an ANOVA. So that's how inference for regularized estimators works, and it's kind of cool if you ask me. And here I just kind of go back through that, describe what I was just talking about. So I won't belabor that. So here is the example for the lasso. And so you can see that variable 3 and 4, which were the KCT and the KTR, those both have p-values of 0 or less than 0.05. It's actually less than 0.01. They just don't print it out. But the p-values for variables 9 and 10, which were the mom's education level, those are not statistically significant. So even though the lasso didn't zero them out, when we consider sampling variability, we would conclude that they're not sufficiently large to be statistically important. They're not statistically significant. And what's really statistically significant are these KCT and KTR, okay? Here we have the ridge regression results, and we get pretty similar findings, right? Here, remember, all the coefficients, we had values for all the slopes, though they were reduced from the original regression. But notice that the only two that are statistically significant are, again, variables 3 and 4, which are KCT and KTR. So they're the only ones that we would say are significantly related to the verbal score. And then the elastic net, very similar story, right? So, and then here's the standard regression. And in this case, we get pretty similar results to what we got from the standard regression model. So what have we learned? Well, when we run regularized estimation, we're going to get the reduced set of variables. But almost always, we're also going to want to know, are they statistically significant? I mean, imagine sending this to a journal, right? You run the analysis, you decide, first of all, hey, I've got a small sample, a lot of independent variables, and regular regression just is not going to cut it for me. So I'm going to use the lasso or net or ridge or one of, all three, but let's say you go with the lasso. Then you run the analysis, you get your reduced set of variables, but you're going to want to know, and the journal is going to want to know, are these statistically significant? In other words, are they different from the slopes, different from zero in the population, even above and beyond whether the lasso selected them or not? And therefore, we need to look at the inference issue. We learned that inference is a problem, right? It's a problem when it comes to regularized estimators, because in order to be correct, it has to account not just for the magnitude of the coefficients, but for the whole variable selection process. And the covariance test does this very nicely for us by comparing the amount of variance in the DV, the dependent variable, that's accounted for with and without our target independent variable, but accounting for this whole variable selection process. Okay. We found that the results for the lasso, the ridge, and the net were all pretty similar. That's by no means always the case, but it happens to be the case here. And it's not super uncommon for that to be true. All right. Well, I hope that was helpful. The last set in this lecture in this series will focus on the issue of running this stuff in R. So I will see you then.